In this video series, we will be covering a topic that causes confusion to many students, and that is the topic of logarithms. Now, before we get into logarithms and the manipulation of logarithms, we have to first cover exponents and exponential rules. Because as you will see, a logarithm is nothing but the inverse operation of an exponent function, which means that all the rules and laws that apply to exponents can be directly translated into the laws of logarithms. Now, if you open the IBAA math guide, you will see that the laws of exponents are covered in SL 1.5 as well as SL 1.7, which also includes the laws of logarithms, the change of base of logarithms, and solving exponential equations, including using logarithms. Now, in this first video, we will cover everything you need to know about exponents and also learn how we can simplify an expression that involves exponents. So if we have a number a to the power of n times a to the power of m, we say that we have the same base here. So a is our base, it's the number that is carrying the power, and n and m are the exponents. So in this case, when we have the multiplication of the same base with different powers or even the same powers, what we do is we add the power. This makes perfect sense if we take an example. Let's say 2 to the power of 3 times 2 to the power of 1, for example. If we expand that, so we have 2 times 2 times 2, that is 2 to the power of 3, and then times 2 to the power of 1, which is just 2. So in total, we are multiplying 2 4 times, so 2 to the power of 4. And hence, we add the powers. Similarly, if we had a to the power of n over a to the power of m, here we subtract the powers, n minus m. Let's look at an example here. So if we had 2 to the power of 3 at the top over 2 to the power of 2 at the bottom, that means we have 2 times 2 times 2 at the top, divided by 2 times 2, and so we simplify. Then the difference is what we will be left with. So here it will be just 2 to the power of 1, which is 2. And so hence the subtraction from the numerator to the denominator. Now, if we have a to the power of 0, this is something that you should know. Anything to the power of 0 is always equal to 1. And if that doesn't seem intuitive to you, think of what it means to have a power of 0. So for example, let's say 4 to the power of 3 divided by 4 to the power of 3. Now, you know that this is equal to 1, right? Because we're dividing by the same thing. Now, if we were to rewrite this in terms of power, we can use the second rule here. And we say, okay, so this is 4 to the power of 3 minus 3. The power of the numerator minus the power of the denominator, which is 4 to the power of 0. And so this is equal to 1. Now, if we have a to the power of n, all of it to the power of m, then we get a to the power of n times m. If you're not convinced, let's look at an example. So let's say 3 to the power of 2, all of which to the power of 3. So what does that mean? That means that 3 to the power of 2 is multiplied by itself 3 times. So we have 3 to the power of 2 times 3 to the power of 2 times 3 to the power of 2. And so in total, if we use the first rule, we have to add the power. So 2 plus 2 plus 2, which basically is 2 times 3, which is 3 to the power of 6. So here we multiply the powers. So these rules apply whether our powers are positive integers or whether they're negative or even fractional. Now let's look at negative and fractional powers just for you to understand what they mean. Now, a to the power of minus n, what that simply means is 1 over a to the power of n. So I like to tell my students, whenever you see a minus, it just means that number doesn't belong here. It's supposed to be somewhere else. And when you put it in the right place, then the minus disappears. And so in the same way, if we have 1 over a to the power of minus m, for example, again, that just means that this a is not supposed to be in the denominator, it's supposed to be in the numerator. So that's a to the power of m. Now let's look at an example to see why that makes sense. So suppose we have 3 to the power of 0, which we know is 1, but let's just write it like this for now, over 3 to the power of 2. Now we know that 3 to the power of 0 is equal to 1, so we know that this is simply 1 over 3 to the power of 2, right? But now let's use the second rule about the subtraction of powers. So this also should equal to 3 to the power of 0 minus 2 which is 3 to the power of minus 2. So you see, 3 to the power of minus 2 is exactly the same thing as 1 over 3 to the power of 2. Now, what about fractional indices? Now, powers don't necessarily have to be integers. Now, I'm sure you're familiar with the square root, which is the inverse of the square operation, and this is simply to the power of a half. Now notice how the square root is the only root where we don't actually write any number here. I mean, you could put a 2 here, but by convention we don't because it is the first root. So it gets to have its own special notation without any numbers on it. But similarly, the cubic root of a is the same thing as a to the power of a third. The seventh root of a is a to the power of 1 over 7. Now, since you know that the square root is the inverse operation of the square, then you should know that the square root of 3 squared, for example, is just 3, because the square root and the square cancel each other out. Now, if we think in terms of powers, what should be the power that we put on 3 squared so that we end up with a power of 1? So it means that we have to multiply 2 by something in order for us to get 3 to the power of 1 at the end. And of course, to get 1, we need to multiply 2 by a half. And so we get 3 to the power of 2 times a half, which is obviously 3 to the power of 1. So you see, the square root is exactly the same as taking to the power of a half. They both cancel out the squaring operation. And this applies to the cubic root, the seventh root, or any root you want to take. Now let's look at a few examples in order to see how we can apply these rules to simplify. Now, what if we have 2 to the power of 4 over square root of 2? We are asked here to write this in the form a to the power of b, which means 2 to the power of something. So the first step is to first convert everything to numbers. So 2 to the power of 4, we leave it as it is. And then square root of 2, that's 2 to the power of a half. So now we've converted the square root into a power. And now we use the second rule, the rule of subtraction, and we get 2 to the power of 4 minus a half. And that is equal to 2 to the power of 7 over 2. Now, what about the cubic root of 4 squared? Again, let's get rid of the root notation and replace it with a power. So we have 4 to the power of 2, all to the power of a third. And here we multiply the power. So we get 4 to the power of 2 over 3. So you see the cubic root of 4 squared is exactly the same thing as 4 to the power of 2 over 3. And what if we had the product, square root of 2 times 2 to the power of 3, and all of that to the power of 4? Now there are two ways to do this. Either we simplify what we have inside and then deal with the power of 4 later, or we can expand the power of 4 and then simplify after. But first, let's get rid of the root and write it as a power. So that is 2 to the power of a half times 2 to the power of 3, all to the power of 4. So what I'm going to do here is I'm going to expand the power of 4 because it's going to simplify the power of a half here. So you should know that whenever you have a power over a product, that you simply distribute the power over everything you have inside. And remember, this is not the case if this was an addition. It doesn't work that way. It only works when it's a multiplication or a division. So here we get a half times 4, which is 2, so 2 to the power of 2, times 3 times 4, which is 2 to the power of 12, and so in total, we add the powers here, so we get 2 to the power of 14. Alternatively, we could have first dealt with what we had inside, so that's 2 to the power of a half plus 3, all to the power of 4, and that gives us 2 to the power of 7 over 2, all to the power of 4, and now multiplying through the 4, we get 28 over 2, which is 14. So obviously, we get the same thing. So the order here doesn't matter as long as you apply the rules correct. Now it is very important to have a solid base when it comes to exponent and exponent operations before getting into logarithms. Now before moving on to the next video, make sure that everything we've covered in this video is very clear to you. Feel free to do more exercises or repeat the exercises that we did before moving on to the next video. See you there!